Welcome to this video on charging and discharging a capacitor. Now keep in mind this is the very basic level. A lot more will be discussed about time constants and all the other time dependent things in an RC circuits video later down the line. So if you haven't watched the first two capacitor videos, I highly recommend you go back and watch that, otherwise this one will not make very much sense. So what I'm going to do here is I have a passive capacitor and I'm going to charge it. So it's charged now, there's an electric field and there's energy stored. And I'm going to disconnect it from the battery, okay? And now when I connect it to something else, I'm going to discharge the capacitor. We won't do that just yet. Let's look at what the actual flow of charge is in this case. The main thing to remember is that nothing is jumping this gap. Electrons are being pulled off of one plate and deposited onto the other, or you could think of maybe holes are being pulled from one plate and deposited onto the other. That would be the positive charge analogy. And so when I charge a capacitor, you can see that the direction of the arrows in the wires shows how the actual charge is being pulled in this one-way sense across the plates, but not between the plates. There's an insulator there and they cannot pass. Now when I'm at this point right here where the capacitor is charged, at this point it has energy stored in it and it has a potential difference across the plates that we could check by just putting the voltmeter across. So I have a potential difference, and I should probably do this. We have a positive potential difference between the plates. And because of that, the minute that I connect this, the light bulb will go off and slowly turn off. So what's happening here, once again, the gap is not breaking. The capacitor charges are moving from one plate through the light bulb onto the other plate. Because there's a potential difference, as we established before, so let's charge it up again. Whenever there's a potential difference, there will be current between those 2 points. In other words, there's an electric field not only between the plates, but also in the wires. And because the electrons can move through the conducting wires, which includes the light bulb, they won't jump the plate, but they'll move through the wires continuously until the potential difference is removed, and then the charge will stop. So when there's current, we see the light bulb on, and the charges are slowly dissipating through here until all of a sudden when they've reached a potential of 0. So it kind of works in the opposite direction to how the charging process worked. Remember, for the charging process, we had work done, charge was separated, so we had a separation of charge. That enabled a potential difference, which remember we said is a cyclical process. So we have to have a potential difference to do work across the battery, and that will cause a separation of charge across the plates, which creates a potential difference across the plates, and then an electric field. Now the electric field that we're going to focus on is the one that's inside the wires. There's an electric field across the plates, but that's not where the electrons move. So because there's an electric field, there's an electrostatic force we could define as Q times E. That force is going to, because there's a potential difference, that force will push electrons, so that will cause a current. When the current is pushed through the light bulb, we see that in the form of energy of light there. But as that's happening, as the current is traversing the circuit, that causes a realignment of charge, or a regrouping of charge, so the opposite of separating charge, which establishes a reverses a potential difference. And once the potential difference is 0, then current stops. And the reason that the current stops is because there is no more electric field. So it's really important to take a look at this. Work is required by the battery. So that potential difference across the battery is required to separate charge in the beginning, which creates more potential difference across the plates, which creates the electric field between the plates, but also in the wires, right, pointing away from the positive. When this is established and you have a non-one-way path now, because the battery, remember, is a one-way pump. When you have a different path that allows the electrons from this plate to move back onto this plate, or conventionally the positive charges to move back to the negative plate, they'll do that because there's an electric field. There's a potential difference across the circuit, and so there is a push of charge. That push of charge is allowing the charges to reconvene or realign with one another, which reverses the potential difference. Once you hit a potential difference of 0, we see that the current is completely stopped in the wires and there's no more electric field because of that, and we're back to square one. In order to have the current move again, we need to charge and then discharge. Now we're going to investigate further on, like I said, in an RC circuit, which is actually what we have in this video. We're going to look at from a more numerical standpoint or quantitative standpoint, how this capacitor is actually time dependent in how long it takes to charge the capacitor and how long it takes to discharge the capacitor. And we'll take a look at that in a later video.